right, so what is motion? And motion is really quite a simple definition. Even the science textbook defines it as changing position, saying that if I go from the trash can to the smartboard, I have changed my position. First, I was at point A, the trash can, and then I went to point B, the smartboard. To change position, you have to be in motion. You can't just magically disappear and appear in two different places. That doesn't, our lives don't quite work that way. Things don't work that way. So to get from point A to point B, no matter what, there has to be motion involved. And in all honesty, everything is constantly in motion, but from where we stand, we can't always see that, which kind of gets into this next point, that an object is in motion if it changes position relative to a reference point. And it's usually best if the reference point is stationary. So right here, you see the stop sign is the stationary reference point. So pretend you're the stop sign here. The car travels past you. It starts here at point A and then moves from point A. Come on. You saw it happen earlier, right? Well, anyway, here we go. It moves from point A to point B over here. And if you were the stop sign, you would say, oh, that car moved. Why? Because it changed position according to where you were, not moving. Now, sometimes we get into if your reference point is moving, it may feel like you are moving. For instance, the school bus here, I don't know if it'll work. The school bus here is, pretend it's driving across the screen, even though my smartboard's not doing it right now. It's driving on the road. Now, if you're in the school bus, from your reference point, let's say where you're sitting inside the school bus, you aren't moving relative to your seat. You are not moving relative to the bus driver. You are not making major movement from one position to another. But in actuality, inside the school bus driving, you are moving from the reference point of somebody outside the school bus. And because of that, it may feel like you are moving as well. So reference point kind of changes whether something's in motion relative to that reference point, which brings us to relative motion, which is kind of what I've been saying earlier. It depends on your point of view. In actuality, everything is in constant motion. Like, I'm looking at my cup on my desk, and even though the cup on my desk, according to my point of view, is not moving, if I could get down to the atoms and molecules that make that plastic cup up, they would be vibrating. They would be moving. No matter what, it's atomic theory. All objects are in motion to some degree, but according to our reference point, a lot of them aren't. So my cup right now is not moving relative to my reference point. So, and another example is kind of down here. Right now, I'm looking at my cup. It's not moving from my reference point. But if I went to the moon or went out in space, my cup would be moving 1,000 miles per hour because that's how fast the Earth rotates. So, is my cup moving? Yes. But according to my reference point, no. And we'll investigate how that kind of matters. But an object is in motion if its distance from a reference point is changing. So we're going to take our definition of motion, changing position, and kind of hone in on it and make it more detailed. So changing position relative to a reference point can kind of be our new definition. And that gets us into scalar and vector quantities. And these are just going to sound foreign to you right now until you see actual examples, but bear with me. A scalar is magnitude only, and a vector is magnitude and direction. And the key thing you want to remember here, when I say magnitude, I'm referring to a number, a measurement. And then when I say direction, I'm referring to north, south, east, or west, and then northeast, southeast, etc. So anytime there's a direction attached to a number, it's a vector quantity. And sometimes when you get into more higher level physics, it's just a positive or negative attached to a quantity, a number, to tell you what direction the object is moving. So the main thing you want to remember to distinguish between these two, because it does get a little confusing, is that vectors always have a direction attached to them. And here are a couple examples. And if you actually notice the scalar quantities, most of the words, especially these first 3 or 4, are pretty familiar to you. Length, area, volume, speed, mass, all should be pretty familiar except for maybe entropy, maybe power, how you measure power. But the vector quantities, there's probably a couple words that you don't know a whole lot about. Displacement, momentum, velocity, lift, drag, thrust, weight. And these all require a direction. You can measure it, you can have a number with it, but you got to tell me what direction they're going. And this is huge with this chapter of physics, is that we're coming down to motion. And vector quantities tell you motion with a direction. I'm going to skip this real quick for the sake of the video. So now we have distance versus displacement. And distance is a scalar quantity, so that's magnitude only, that answers the question of how far you actually go from a reference point. So it's a length, basically. Measured in meters is its base unit. Then we have displacement here. Displacement is a vector quantity that answers how far, so the distance, and in what direction from a reference point. So both of these are answering the question of how far. So when I ask you to compare them, you can say that displacement has to do the direction. It's a vector quantity. And if we look, it's kind of like saying that I don't know, let's say you live on a square block and you go halfway around the block to a friend's house. Now, technically speaking, let's see if I can draw a picture here. Let's get a square going. So you live on this block and let's say you live right here and you want to go here and then go here to a friend's house who lives, so you start here, that's point A, and you want to go here to point B. Now, the distance you traveled, how far you traveled, was the length of this plus the length of this. But when we get into displacement, how would you describe your location, starting location, in relation to your ending location? It would probably be a lot shorter than the actual distance you went. And how would you describe the direction of your friend's house? You wouldn't say the direction is south and then east. You would just say it's southeast. So that's where we get into the difference between these two terms. Here's another picture to illustrate it. Say this is the distance somebody walked. The distance they walked, they went in all kinds of directions. But when, let's say they were going from point A to point B, and this is the route they took. If a friend asked them what direction they were from their starting point, they would say southeast, even though they kind of went southeast and a little south and north and southwest. They kind of went all different directions. But total, the distance from point A to point B that they traveled is a lot shorter than the distance they actually traveled. So that's where we refer to it as their displacement. From point A to point B, they went southeast, a much shorter distance than the distance they actually traveled. And here's another example with a mouse. The mouse isn't very smart. The cheese is right in front of him, but he decides to do this loop-de-loop course. Now, he went a lot more distance than what he actually displaced. And he, again, displaced in the southeast direction in a much shorter distance than what he actually traveled. So the final position here of the mouse depends on both the distance it traveled and the direction it went. And that's where we get into displacement. So that's all I have for today. But after this, I want you to watch the next video that's posted, which kind of elaborates more on this whole distance versus displacement thing.